Hello everyone, welcome to today's lecture on variational formulation in the course Finite Element Methods and Analysis. I am Rajesh Kumadi from the Department of Automobile Engineering, SNS College of Technology, Coimbatore. Today's topic is one of the most important mathematical foundations you will learn in element analysis. Variational formulation is the bridge that connects continuous mathematical equations to discrete computational methods we use in real engineering software. By the end of this lecture series, you will understand how engineers convert complex differential equations into simple matrix equations that computers can solve efficiently. So let us begin our journey into the fascinating world of variational formulation. So in this slide, we can see about the strong form and the weak form. The strong form is also called the classical approach or differential form. In this approach, we require our solution to satisfy the governing partial differential equations at very single point within the domain. Let us emphasize this every single point. For example, if we have d, d square u by dx square plus f equal to 0, the solution u must satisfy this equation exactly at x equals 0, at x equals 0.001, at x equals 0.5 and at x equals 1, literally at every point in the domain. This is extremely demanding requirement. Why? Because it necessitates continuous derivatives of order n. For a second order equation, we need second derivatives to exist and be continuous everywhere. This makes the finding exact solutions very difficult, and for complex geometries like a car chases on aircraft wing, it becomes practically impossible. The strong form demands governing partial differential equations must be satisfied point-wise, boundary conditions must be satisfied exactly, high continuity requirements throughout the domain. Next is the weak form. It is the integral approach. Now, the weak form takes a complete different approach. It is also called the integral formulation. Instead of demanding that our equations be satisfied at every individual point, the weak form requires the equilibrium be satisfied on an average across the domain. Think of it this way. Instead of balancing forces at every single point on a beam, we are saying let's balance the total force over the entire beam. This is a weaker condition, hence the name weak form. The mathematical magic happens through integration. We multiply our differential equation by a test function and integrate over the domain. This process fundamentally changes the requirements. The weak form gives an integral statement of equilibrium, average satisfaction rather than point-wise satisfaction, reduced derivative order from order n to order n by 2, mathematically equivalent to the strong form. The key advantage. Why this matters? Because it enables to use simple polynomial functions for approximation. We can use linear functions, quadratic functions, simple piecewise polynomials. This is the fundamental reason the finite element method works. Both forms are mathematically equivalent. They give the same answer, but the weak form is infinitely more practical for computation. This transformation from strong to weak form is the major step in the finite element method. Principle of virtual work. Now, we can understand weak formulation mathematically. Let us connect into principles. The principle of virtual work provides the physical motivation behind the variation formulations. This principle beautifully connects abstract mathematics to tangible engineering concept. Let us see the four key steps. The first step is the virtual displacement. Imagine applying fictitious imaginary displacements at every point in your structure. We denote these as delta U. These are not real displacements, they are hypothetical. What if movements? Think of it like this. What if I moved this point from a tiny amount to what I shifted that point slightly? These virtual displacements must satisfy two conditions. They must be small, infinite, similarly small. They must be arbitrary. We can choose any pattern we want. They must be compatible with boundary conditions. Next is the step 2, that is the internal virtual work. When we apply these virtual displacements, the structure deforms slightly and this creates virtual strains. These internal stresses in the material do work through these virtual strains. We calculate this internal virtual work as integral of sigma into delta E into dV. This represents the total energy stored in the material due to deformation. Think of it as energy in a compressed spring. When you compress the spring virtually, you are doing work against the internal spring force. Next is the step number 3, that is the external virtual work. At the same time, the external forces acting on the structure also do work on when we apply our virtual displacements. We compute this external virtual work as integral of B into delta U into dV plus integral of T into delta U into ds. Here, if you see, the B represents the body force, right? Such as gravity or magnetic forces. And these act through the volume. Example, weight of the structure itself. And you can see the second term, the T represents the surface tractions. These act on a surface, yes. Example, pressure on a surface, applied loads. This external virtual work accounts for all external loads, both distributed throughout the body and applied on the surface. Step number 4, equilibrium condition. The powerful statement now becomes the principle itself. For a structure in equilibrium, the internal work must be equal to external virtual work for any virtual displacement. Let me empathize. This must be true for any arbitrary virtual displacement we choose. This is the universality what it makes so powerful.